Nuclear winter is a hypothesized global climatic effect most often considered a potential threat following a countervalue nuclear war. As a result of city and natural wildfire firestorms, it is most frequently suggested to manifest as a result of the combined combustion pollution from the burning of at least 100 city-sized areas at firestorm intensity. The term was specifically coined to refer to computer model results where this smoke remained for years, or even decades, and caused massive planet-wide temperature drops for as long as it remained. The climate models in the public domain suggest that the ignition of 100 firestorms, comparable in intensity to that observed in Hiroshima in 1945, would produce a small nuclear winter. The burning of these firestorms would result in the injection of soot into the Earth's stratosphere, producing an anti-greenhouse effect that lowers the Earth's surface temperature. The models conclude that the cumulative products of 100 of these firestorms would unmistakably cool the global climate by approximately 1 degree Celsius, largely eliminating the magnitude of anthropogenic global warming for 2 to 3 years. The authors speculate, but do not model, that this would have global agricultural losses as a consequence. A much larger number of firestorms, however, were the initial focus of the computer modelers that coined the term in the 1980s. These were speculated to be a result of any countervalue city airburst nuclear weapon during an American-Soviet total war. These larger firestorms were believed to cause nuclear winter conditions for as long as a decade, with summer cooling by about 20 degrees Celsius in core agricultural regions of the US, Europe, and China, and by as much as 35 degrees Celsius in Russia. This cooling was produced due to a 99% reduction in the natural solar radiation reaching the surface of the planet in the first few years, gradually clearing over several decades. As nuclear devices need not be involved in the ignition of a firestorm, the term is a common misnomer. This is due to, in greatest part, the vast majority of published papers stating, without qualitative justification, that nuclear explosions are the cause of the modeled firestorm effects. The only phenomenon that is scrutinized and computer-modeled in the nuclear winter papers is the climate-forcing agent of firestorm soot, a product which can be ignited and formed by a myriad of other, more common, means. On the fundamental level, it is known that firestorms can inject soot smoke aerosols into the stratosphere, as each natural occurrence of a wildfire firestorm has been found to, surprisingly frequently, produce minor nuclear winter effects, with short-lived, almost immeasurable drops in surface temperatures, confined to the global hemisphere that they burned in. This is somewhat analogous to the frequent volcanic eruptions that inject sulfates into the stratosphere and thereby produce minor, even negligible, volcanic winter effects. A suite of satellite and aircraft-based firestorm soot monitoring instruments are at the forefront of attempts to accurately determine the lifespan, quantity, injection height, and optical properties of the smoke. Information regarding all of these properties is necessary to truly ascertain the length and depth of the cooling effect of firestorms, independent of the nuclear winter computer model projections. Presently, from satellite tracking data, stratospheric smoke aerosols are removed in a time span under approximately 2 months. The existence of any hint of a tipping point into a new stratospheric condition where the aerosols would not be removed within this time frame remains to be determined. Mechanism. The nuclear winter scenario assumes that 100 or more city firestorms are ignited by the nuclear explosions of a nuclear war, and the firestorms lift large enough amounts of sooty smoke into the upper troposphere and lower stratosphere. Soot lifted by the movement offered by the pyrocumulonimbus clouds that form during a firestorm, at 10 to 15 kilometers above the Earth's surface. The absorption of sunlight could further heat the soot in the smoke, lifting some or all of it into the stratosphere, where the smoke could persist for years. If there is no rain to wash it out, this aerosol of particles could heat the stratosphere and block out a portion of the sun's light from reaching the surface, causing surface temperatures to drop drastically, and with that, it is predicted surface air temperatures would be akin to, or colder than, a given region's winter for months to years on end. The modeled stable inversion layer of hot soot between the troposphere and high stratosphere that produces the anti-greenhouse effect was dubbed the smokosphere by Stephen Schneider al. in the 1988 paper. Although it is common in the climate models for the city firestorms to be ignited by nuclear explosions, they need not be ignited by nuclear devices. More conventional ignition sources can instead be the spark of the firestorms, as prior to the previously mentioned solar heating effect. The soot's injection height is controlled by the rate of energy release from the firestorm's fuel, not the size, or lack thereof, of an initial nuclear explosion. For example, the mushroom cloud from the bomb dropped on Hiroshima reached a height of 6 kilometers within a few minutes and then dissipated due to winds, while the individual fires within the city took almost 3 hours to form into a firestorm and produce a pyrocumulus cloud, a cloud that is assumed to have reached upper tropospheric heights as over its multiple hours of burning. The firestorm released an estimated 1,000 times the energy of the bomb, while the firestorm of Dresden and Hiroshima and the mass fires of Tokyo and Nagasaki occurred with mere months separating them in 1945. The more intense and conventionally lit Hamburg firestorm occurred in 1943. Despite this, these 5 fires potentially placed 5% as much smoke into the stratosphere as the hypothetical 100 nuclear-ignited fires of modern models. While it is believed that the effects of the massive soot emitted by 100 firestorms would have been detectable with technical instruments in World War II, only 5% of that would not have been possible to observe at the time. Aerosol removal timescale: the exact timescale for how long this smoke remains, and thus how severely this smoke affects the climate once it reaches the stratosphere, is dependent on both chemical and physical removal processes. The most important physical removal mechanism is rainout, both during the fire-driven convective column phase, which produces black rain near the fire site, and rainout after the convective plumes dispersal, where the smoke is no longer concentrated and thus wet removal is believed to be very efficient. However, these efficient removal mechanisms in the troposphere are avoided in the Robock 2007 study, where solar heating is modeled to quickly loft the soot into the stratosphere, detraining or separating the darker soot particles from the fire cloud's whiter water condensation. Once in the stratosphere, the physical removal mechanisms affecting the timescale of the soot particles' residence are how quickly the aerosol of soot collides and coagulates with other particles via Brownian motion, and falls out of the atmosphere via gravity-driven dry deposition, and the time it takes for the phoretic effect to move coagulated particles to a lower level in the atmosphere, whether by coagulation of the phoretic effect. Once the aerosol of smoke particles are at this lower atmospheric level, cloud seeding can begin, permitting precipitation to wash the smoke aerosol out of the atmosphere by the wet deposition mechanism. The chemical processes that affect the removal are dependent on the ability of atmospheric chemistry to oxidize the carbonaceous component of the smoke, via reactions with oxidative species such as ozone and nitrogen oxides, both of which are found at all levels of the atmosphere, and which also occur at greater concentrations when air is heated to high temperatures, which will be discussed later. Historical data on residence times of aerosols, albeit a different mixture of aerosols, in this case stratospheric sulfur aerosols and volcanic ash from megavolcano eruptions, appear to be in the 1 to 2 year time scale. The satellite tracking of wildfire smoke aerosols from the 17 North American pyrocumulonimbus cloud injection events in 2002 indicates that the aerosols are removed in a time span under approximately 2 months, although the exact mechanisms by which they are removed, and the existence of any hint of a tipping point into a new stratospheric condition where the aerosols would not be removed within this time frame, remains to be experimentally determined. Aerosol-atmosphere interactions are still poorly understood. Soot properties. Sooty aerosols can have a wide range of properties, as well as complex shapes, making it difficult to determine their evolving atmospheric optical depth value. The conditions present during the creation of the soot are believed to be considerably important as to the final properties, with soot generated on the more efficient spectrum of burning efficiency considered almost elemental carbon black, while on the more inefficient end of the burning spectrum, greater quantities of partially burnt, oxidized fuel are present. These partially burnt organics, as they are known, often form tar balls and brown carbon during common low-intensity wildfires, and can also coat the purer carbon black particles. However, as the soot of greatest importance is that which is injected to the highest altitudes by the pyroconvection of the firestorm, a fire being fed with storm force winds of air, it is estimated that the majority of the soot under these conditions is of the more oxidized carbon black nature. Consequences. Climatic effects. A study presented at the annual meeting of the American Geophysical Union in December 2006 found that even a small-scale, regional nuclear war could disrupt the global climate for a decade or more. In a regional nuclear conflict scenario where two opposing nations in the subtropics would each use 50 Hiroshima-sized nuclear weapons on major, populated centers, the researchers estimated as much as 5 million tons of soot would be released, which would produce a cooling of several degrees over large areas of North America and Eurasia, including most of the grain-growing regions. The cooling would last for years, and according to the research could be catastrophic. Ozone Depletion. A 2008 study by Michael J. Mills and co-authors, published in the Proceedings of the National Academy of Sciences, found that a nuclear weapons exchange between Pakistan and India using the current arsenals could create a near-global ozone hole, triggering human health problems and causing environmental damage for at least a decade. The computer modeling study looked at a nuclear war between the two countries involving 50 Hiroshima-sized nuclear devices on each side, producing massive urban fires and lofting as much as 5 million metric tons of soot about 50 miles into the mesosphere. The soot would absorb enough solar radiation to heat surrounding gases, causing a series of surface chemistry reactions that would break down the stratospheric ozone layer, protecting Earth from harmful ultraviolet radiation. Nuclear summer. A nuclear summer is a hypothesized scenario in which, after a nuclear winter has abated, a greenhouse effect then occurs due to CO2 released by combustion and methane released from the decay of the organic matter that froze during the nuclear winter. It is supported scientifically far less than nuclear winter as a risk.